Thanks to the organizers for inviting me to give a different talk. Because when the invitation was sent almost a year ago, the organizers didn't know anything about the detection, but we didn't know anything about the detection either. So they invited me to give basically a predictions talk, and I guess this is what they had in mind when they invited Stan, but I can tell you, Stan, that having given a lot of predictions LIGO talks over the years, and having now gone through this transformation, it's much better to be talking about these discoveries. So I'm giving this talk on behalf of the combined collaborations of LIGO and Virgo. And I'll tell you very briefly about the discovery, but I'll focus for this part of the talk on the astrophysics and astrophysical implications. So before I get started, though, I have to say that the fact that I can stand here and tell you about the discovery is all due to the instrumentation scientists and engineers who were able to make these detectors able to make these measurements. So I just want to point out in a slide that doesn't do justice to all the instrumentation work that basically we have had, since initial LIGO, we have had a number of improvements for the detector. Increased laser power, bigger mirror masses, better mirror coatings, and improved seismic isolation. And this is how the noise curve improved from where we were in 2010-11 with the last run of initial LIGO, which had beat expectations, design sensitivity. And this is where we were when we turned on last September. So this is about a factor of 3 here and a much bigger factor at lower frequencies. And it's this jump in sensitivity that made the discovery possible. I can't, it's like looking at photographs of my firstborn or something like this. So we do call it our firstborn, by the way, within the collaboration. So here's the signal. You can see it in a frequency time domain. You see this little banana here in the 2 detectors, and you can see it by eye on these plots. The frequency is increasing as a function of time, and the fact that it becomes whiter, the amplitude is increasing, and this is your signature of a chirp-like signal. The direct data with the broadband noise removed is what you see under, and again, you can see the oscillations and the increase in frequency by eye. Not all detections are going to be like this. Be prepared. Okay, so I won't spend any time for how the search actually is done in the data. I'll just show this one plot just to point out that basically this is the event, GW150914, and it is basically at more than 5 sigma significance after we study our background noise. The signal is in great agreement with relativity, which is the light color curves on top of the data. And in addition to that, in the data we have reported already, there's a second event. It's not an event, it's a second trigger, which is down at 2 sigma, basically, given our data analysis. And you cannot claim it as an event, but we have reported that it has parameters consistent with a binary black hole, and it plays an important role when we try to extract a rate from this data set. But what I will do for this talk is actually focus on what do we do after detection? How do we extract, not how, I will not even explain how we do it in any detail, but I'll tell you about the physical parameters we can extract from the signal and what does it mean about astrophysics. So in terms of the actual analysis, and I should say that I've been a member of this collaboration for 16 years now. For a few months while I was here, Harvard had a LIGO group. It was me and Chris Belczynski, my student at the time. And then I moved to Northwestern. And initially, about half of my years in the collaboration, I worked on predictions, astrophysical predictions for what the detectors will see. But the rest of the second half, we've been focusing in my group on exactly this problem. How do you extract the physical parameters for the system, especially if you have spins? So the way we do it is basically we use Bayesian methods that allow us to do stochastic sampling on a very high dimensional space. The space is what defines the waveform, which we cross-correlate with the data, and we sample this likelihood variation in this space. We have 2 different stochastic samplers, and we also use 2 different binary coalescence waveforms, as well as a collection of sine Gaussians, which is basically a generic waveform. It doesn't even have to be you don't have to assume you are dealing with a binary coalescence to extract the parameters of this signal. And the results agree basically for all of these analyses. What are the results? Well, I'm sure you've seen a lot of these, and it was mentioned in other talks. The masses are on the high side, above our expectations or past measurements from X-ray binaries. And what we measure primarily is actually the chirp mass, which is the width here, that's the error in the chirp mass. And this is a line of constant chirp mass in the M1, M2 plane, primary and secondary, and then you can project in each dimension and get a probability distribution function, a measurement for each individual black hole. What truncates the constant chirp mass curve here is basically the ending frequency, along with a little bit of information in the frequency evolution of the signal. Then with these 2 individual masses, if we then compare us, accept that we are dealing with a binary coalescence signal and compare to numerical relativity results, we can place tight constraints on the mass of the final black hole and the spin of the final black hole. And this spin measurement, it seems high, about 70, 60+% of the maximum spin a black hole can have. But it's actually consistent with 2 non-spinning black holes coming together. So you get this generically, this result of about 65% just because of orbital angular momentum conservation. Now, we try also to place constraints on the individual spins of the black holes. And what we can say for this particular system is the following. We can tell that if we only look at the spin component aligned with the orbital angular momentum axis, we can place a tight constraint on the limit, an upper limit, and say that spin aligned with the orbital angular momentum axis are constrained to be small, smaller than, let's say, 0.2 or so of the maximum spin. In the plane, for the component of the spin perpendicular to the orbital angular momentum axis, we actually cannot derive any constraint. Basically, we recover our prior, which means we can't tell how big the component of the spin in the plane is. So overall, it's very hard for us to constrain, at least for this system, to constrain the spin magnitude. All we can say is that along the axis here, this is a different representation of the same results, along the axis we have small spins. Now, I don't know if Doron is still here, I think he left, but you can use spin measurements under certain formation scenario for binary black holes and draw conclusions about the formation of these black holes. And that's an interesting path in terms of astrophysical interpretation. We'll see what the data tell us when we have a lot more of these. I mentioned rate earlier. With one event, you cannot make a rate estimate, but with one event and a trigger, you can. And of course, the rate is, guess what? With 2 double neutron stars, the rate predictions were very wide. Well, with potentially 2 binary black holes, the rate constraint is not great. But compared to, in these units of events per cubic gigaparsec per year, we are somewhere between a couple and a few hundred events. And we can already exclude model predictions that were giving you rates less than about 1 per cubic gigaparsec per year. So the low end of the rate predictions are now excluded. Notice that I'm not describing the plots in detail. Basically, the rate prediction also depends on whether you're using only the detection or you're also using the trigger. If you get the combined rate, that's the blue curve, and you can see that it's almost on top of the red curve. And that means that basically currently our rate is actually dominated by the non-event. Okay, our rate prediction. But if you assume a broad mass distribution, then you can get a few slightly different constraints, and that's the other plot. Rate of binary black hole mergers. So the assumption is here that the 2 event and trigger are representing the whole population, obviously not very well, you have only 2 draws. Here, you assume you know the mass distribution, some power law or an IMF-like or some flat distribution, and then you can extract the rate. But we quote rates for the full binary black hole population, not just the massive stuff, okay? All right, distance is of interest, of course. We have a significant uncertainty primarily because the way the signal and the polarization, the 2 polarizations get recorded on our detectors, we end up with a strong correlation between distance of the signal and the actual inclination of the binary, okay? So you have this V-shaped correlation, and basically we have a large error bar in the distance. And of course, you know, many of you know, because many of you followed up this event, that it's very hard to localize something with 2 detectors only. So we have this big banana here. When I gave the first public talk on the event, somebody from the audience told me the sky is smiling at you. So we take it this way. Eventually we'd like smaller smiles, but you know, we'll get there. All right, so the event was followed up by a large number of groups that had an agreement with the LIGO collaboration to receive triggers. There was follow-up over many tens of days in X-rays, optical, and radio. Overall, every group has reported an upper limit, except there is a potential claim of a Fermi Gammaray Burst counterpart, although the study is still under review for the journal. But of course, immediately with the rumor of a potential counterpart, when you don't expect one from 2 binary black holes, as Brian said earlier today, the question came up, how could you get an electromagnetic counterpart? So Avi and his older students, not together, jumped to provide potential explanations. Now, these are I won't go into the details. I think Brian described some of them. There are some doubts on whether the signal is actually real, and there are some debate, I would say, whether some of the models are actually possible to be giving a gamma-ray burst, but I think this is an interesting path, especially if we have more detections with electromagnetic counterpart claims. I do want to show you that this is the sky location. You get this big ring you get on the sky. Normally you would get a full ring from 2 detectors, but because we have a little bit of polarization information, you actually can break the degeneracies and break the big ring into an arc. If you had Virgo, this particular system with these masses, this SNR, etc., would have been localized down to the green circle with Virgo and with India down to the red circle, going down to about 10 square degrees. Okay, so this is one big reason why we need more detectors. And this plot, I think, was shown by Brian earlier, a study that we did some years back with my graduate student to basically show how well we can localize things if we had 3 detectors at design sensitivity. And you can see you have the full rainbow colors here. So, but the median in this analysis with Virgo, I don't say it here, where is it? I say 3 detectors. The median is about 10 square degrees. If you add India, which is now approved and it's going to go ahead in less than 10 years, which doesn't seem that far away. All the patches are red, so we're down to a few square degrees. Okay, astrophysics. So first of all, I want you to just take a step back and realize this is the first observational evidence for the existence of a binary black hole. They've been predicted for many decades, but we didn't know they existed. It also provides very strong existence that actually black holes, in agreement with general relativity, exist. Now, they are heavy black holes, and that has implications, as Stan had mentioned in a broader context in his talk, has implications about metallicity. So what you can do is look at the most current models, stellar evolution models from single stars, to see what predictions are giving us for black hole masses versus progenitor masses at different metallicities. And I won't go through these plots in any detail. They come from two different groups that I miss putting Belczynski et al. Here and Spera et al. On the right. And they differ because you really don't know how black holes are forming. Stellar winds are not exactly well understood, et cetera. But you can set a conservative limit that if you want to explain the mass of the lowest end of the mass of the binary black hole, then you must be forming these black holes from subsolar stellar progenitors. A very conservative limit is a factor of 2 subsolar. Depending on the model, you go down to even a 10th subsolar. All right, so let me now transition to how these systems might have formed. As I said, they've been predicted over the years in different incarnations and sophistication of model predictions, but there's two main paths. One is that you can either form binary black holes from isolated binaries. They can come from low population all the way. They've been studied as POP3, with POP3 progenitors, or you can form them through rapidly rotating stars in isolated binaries. A completely different way of forming your binary black holes is through dense stellar clusters. In globular clusters, young clusters, galactic centers, you can have collections, individual black holes that sink in the center, and through dynamical interactions, they start kicking each other out, but also forming binaries that can eventually merge. You've heard a lot in different talks throughout this conference about how binary compact object time delay or merger time distribution follows 1/tau. This is not true for all the formation models, and it will have implications for us trying to figure out which path might be dominating. A quick flash of the literature of isolated binary black hole formation from isolated binaries. I'd like to make a couple of points. Tutukov and Jungelson in 1973, this is before Halston-Taylor was discovered, discussed isolated binary evolution and predicted that binary black holes can form. They didn't talk about mergers. It's a Russian article, but we have Russian members in the LIGO collaboration, and they translate it for us. And then it was really in the late 90s that people started studying binary compact objects and specifically binary black holes in some quantitative fashion. So a lot of the work has been done by many groups, myself included, students, et cetera, all the way around 2010. It was only after 2010, all the way up to this year, before the discovery, where people realized that massive black holes, like the 30, 40 solar masses we're seeing in this discovery, can form. So it's important to remember that actually these kinds of binary black holes have been predicted in the literature for the past 5 years. And the reason is that our best understanding, and I'll certainly share the comment Stan made, we really don't know how strong the winds are, but our current best empirical understanding is that the winds are weakened compared to the old models, and also people started studying different star formation environments. Now, I'll go through the different formation paths, not in detail, but the punchline is I want to demonstrate that all three main formation paths, isolated binaries, regular, isolated binaries with rapid evolution, rapid rotation, and dense stellar clusters, they all make predictions consistent in rates and in masses with the one discovery. Okay, so right now, no particular formation path is being favored. So regular binary evolution, variations of this plot you've seen multiple times through the conference, but basically involves mass interactions, common envelopes, formation of one black hole, eventually formation of the second black hole. Mass predictions, an example of a prediction, this was from a paper, it's actually from the 2012 paper, and you can see chirp masses all the way to about 30 solar masses, and the prediction, this is just one model, 1/10 of a solar metallicity, and the detection agrees with this kind of prediction. Rapid rotation, this is a more recent formation path that was put forward in this context actually very recently by Selma and Ilya Mandel and also other collaborators in parallel. But the basic idea is that your massive stars, because they're rotating very rapidly, they become chemically homogeneous, they don't expand. That means you get rid of all the pesky astrophysics, no common envelopes, mass transfer, etc. But you need to have your star in very rapid rotation and eventually form your black holes and not break up your binary. So it can be done. Rate predictions and masses, very much consistent. These are total masses at about 6+ and mass ratio close to 1. That's where the discovery is. Okay? Generically, without any fine-tuning of the modeling. Dense clusters. The modeling there has had a longer, not longer, but more of an evolution. People started doing pure black hole dynamics in the 90s. Then there were a few studies with binary evolution and Mickey Mouse dynamics, I call it. Then eventually, only around 2010, we were able to combine stellar dynamics and binary evolution at the full sophistication level we can do either on its own. And people also have studied binary black hole formation in galactic centers and in young star clusters. Punchline, showing a few examples. These particular examples happen to be from our group at Northwestern. Again, the punchline message is that whatever stellar dynamics predictions you look at, masses and rates are consistent with the event. You can see that stellar dynamics can form things all the way to high redshift. In terms of mass distributions, you're really very much consistent with the two events we have now. And the black holes here, you don't have complicated binary evolution, but you do have a very complicated, elaborate stellar dynamics history in terms of exchanges and breakups, etc. So our astrophysical conclusions, but I'm not done yet. The key points is that we now know heavy black holes exist in merging binaries. Their formation points to subsolar metallicities given the masses. We can form them through a variety of formation channels that have been discussed in the literature. Right now, we cannot distinguish between the channels, but low rate predictions are excluded. So let me very quickly just highlight quickly address the question of how could we distinguish between different formation paths. Not just with this discovery, but down the road with more of them. It's potential. One possibility is that mass ratios have different predictions for different models. Here's an example of mass ratios from clusters without dynamics and from clusters. And you can see a systematic difference. But the problem we're having is that to measure the mass ratio of one individual system is very hard, and our error bars are big. For this one system, we only have a lower limit. Spins, I mentioned briefly, there are implications from the spins if we can not only measure the magnitude, but also their orientation. The stellar dynamics path gives you black holes with spins oriented all over the place, okay? But binary evolution should give you spins aligned with orbital angular momentum axis. So having a sample and being able to set some constraints on the spin tilts might give us a handle over this question. More importantly, I think, and that would be my guess right now, is that eventually with a large sample, we will be able to be probing the rate evolution as a function of redshift. And the time delay between formation of binary black holes and merger for the different formation channels is different. So 1/tau, you heard about it, but this is only for classic isolated binary evolution. Globular clusters have actually more systems at longer merger times, and the high rotation systems also has a different distribution. That, combined with cluster formation as a function of redshift, etc., will lead to different rate evolutions as a function, merger rate evolution as a function of redshift. But we'll need a big sample. I'm going to end with a a look into the future and mention that actually, and possibly I'm looking for Alberto, but hopefully Alberto will spend more time on this. But Alberto, I'm going to show your plot anyhow because it's so nice. So this one system, this is the black line. This is where it was in LIGO. It would have been detected by LISA about 10 years before merger. LISA will be able to be detecting these heavy binary black holes. We had not realized that. What does this mean? It means that we'll be able to probe their properties in this regime, and actually, in terms of distinguished formation paths, we are finding these are unpublished results from our group, that eccentricities in the LISA band are measurable and high if the binary black holes come from stellar clusters. And if they're coming from isolated evolution, they're not. They're very small. And in fact, you can even separate the two main paths of stellar evolution here in the two bands. I don't have time to expand on that, but obviously, we're very much excited about what's coming. This is just the beginning for us. We will be improving the detector sometime in late summer or September. We're going to go online again for O2, which we think will have sensitivity, significantly better sensitivity as a function of total mass for binaries. And eventually, we'll be seeing potentially massive black holes. We'll see, Stan. We have now a challenge from you, because this is the only way to see whether, I think, clearly measure individual black hole masses above 50 solar masses, above 55 solar masses, and see what happens with these massive stars. But we'll be able to see them out to cosmological redshifts by design sensitivity. What should you expect in terms of numbers? Am I completely out of time? Yes, I am. Well, but I'll get this question anyhow. I always get this question, so I might as well show the answer. So, one event and one trigger, you can take the median rate from that prediction, look at our sensitivities as expected in the next 3 runs. We have finished O1, but we haven't reported all of O1. You can see that the probability of, in the rest of O1, having more than 0 detections is about 90%. And we know what the sensitivity of O1 was. O2, we don't know what the sensitivity will be, somewhere in the purple band, but 100% probability we should have more than 5 if we're at the optimistic end, as we were with the O1. And then we go into several tens of events as we move forward towards design. So I'm going to stop here. Thank you.
Very fascinating talk. I have a somewhat pedantic question that you didn't touch on but is interest to me. It was reported that the 2 black holes individually have masses of 29 solar masses and 36 solar masses, giving a total of 65, and that the merged black hole has 62, and therefore 3 solar masses worth of gravitational waves came out.
Yep.
And from that, I assume one was able to calculate the distance from estimating the intensity of the event, the gravitational waves we observed here.
Yes.
That's all speculation on my part, but I think it's reasonable.
You're right, yes.
The one thing that I'm unclear on is that the errors associated with the estimates of the individual masses and the combined masses are larger than the 3 solar masses worth of gravitational waves that's supposed to come out.
Yes.
So my question is, I'm finally getting to it, I conclude, therefore, that the correlation between the estimates of the individual masses must be very high.
Yes.
And I was wondering if you have a correlation matrix that you could describe.
So you're absolutely right. You asked a question and you answered your question. I'm not complaining, and I don't have a correlation matrix to show you, but it's basically shown here. Not quite what exactly you would like to see. I don't have a plot for that. But basically, the 2 individual masses are highly correlated into this band, diagonal band, and along this band we have a constant chirp mass, but also we see the end of the signal, and the ending frequency in the gravitational waveform is very closely associated with the total mass of the system. So that we can constrain better than the individual masses. Chirp mass and total mass. Total mass worse than the chirp mass, but still better than individual masses. So that's how we get those smaller error bars for how much mass was emitted in gravitational waves.
With respect to the channel that leads to these binaries, the dominant channel, you didn't mention one other approach to go at it, and that's to look for progenitors within the Milky Way galaxy or the nearby universe. In other words, can we find those binaries that will end up within the Milky Way galaxy that will end up as these systems?
Yeah, so we could do this, and people have tried it in different variations. I mean, there are, for example, there's high mass X-ray binaries where people have said, look, this system will become a binary black hole, but not that high mass. That's not this high mass. So, well, in our galaxy and the nearby universe, we're not at, well, you might say if you only need half solar, then you can do it in the nearby universe. But in our galaxy, we don't have large populations of young stars at half solar metallicity. So you're not going to see very massive, that kind of massive stars. Also by number, they're of course a very small fraction in the IMF. But there's a couple of X-ray binary systems that have been claimed to have, at least one has been claimed to have a very high mass black hole, which was in this regime, I think in the 30 pluses. But since then it's not a dynamical mass measurement. So if it's real, then it would be a progenitor to these massive black holes. Otherwise, I think the rarity of these very massive stars, combined with the need for low metallicity, potentially as low as 1/10 for some models, I think is what prevents us from finding these stellar progenitors.
This event was a greater than 5 sigma event. Is there ever going to be any exploration of, say, any 3 sigma events that might be in the O1 data?
So for each data set that we'll be reporting on, we will give the full range of triggers that don't pass the cut for a detection. Now, as we have more and more detections, we will not require a 5 sigma, which is kind of an arbitrary cut and comes from particle physics, etc. So one can debate whether 5 sigma is the magic number, but I think you'd like to see at least 3, 4 sigma. I can tell you with certainty that in this data set of 16 days, there was nothing between 5+ sigma and 2 sigma. Okay? But yes, as we report on data sets, we will report the low significance triggers as well.